All right, didn't really receive any questions via email. Didn't really see any questions in terms of the discussion boards. Do keep in mind your exam is this weekend. So the advice I'll give you with exam one, the discussion boards are very representative of a few of the free response problems. And the number of questions on these exams are going to start getting smaller and smaller because material is going to get more and more focused. So make sure you're doing the discussion boards and understand them. Make sure you're doing the homework and you understand. Making sure you're doing the review packets that are on the course website and understanding them. Now, this week is also the withdrawal week. So technically, as of I think today is the last day to withdraw the course without it affecting your GPA. This is a W versus a WF. If you take the exam, I'll be grading the Monday, and let's say I'm going to be perhaps I'll be generous and not do the attendance until like Tuesday. If you see your exam grade and you go, I don't think I can pass this course, I really don't want this affecting my GPA, shoot me an email by Monday afternoon and say, hey, I really think I'm going to withdraw from the course. This way I can legitimately put you in as having withdrawn before the WWF date. If you wait until the end of next week and go, hey, I really like my grade in the class, I really just kind of want to drop it, but I want to take an F, at that point I've already entered the attendance. So again, take your exams this weekend, take them seriously. Um, Keep in mind with the exams, like I need to grade them, so the same rules apply. Check to see if your work's been graded before you get email questions about your grades. But the goal here is by Monday by about noon to have all the grades entered in. And again, I think I can be generous and kind of just procrastinate on entering the attendance in until like Tuesday. But do shoot me an email. Once you do the discussion board for next week, you're in the course. So you're in for the WWF date. Again, the discussion boards, they don't really get graded until like Thursdays. So again, like just kind of be judicious if you're thinking about dropping the course. So right now I'm seeing 0 concurrent viewers on this live stream. Again, remember, these are not lectures. These are office hours. If you have questions, you need to send me questions, but these are not meant as a lecture. I already have videos for those on the course website. So I'm going to leave the chat menu up. If you got questions, feel free to ask. I'm spend about 4 or 5 minutes checking on a few things and responding to a few unrelated texts. But other than that, this is your time. Again, remember your exam is this weekend. It opens up this weekend. So this is the third of 4 exams. Oh, I do want to bring a comment about the final exam. The final exam is supposed to be given through a proctored center. There right now, the one on Southern Wake campus is closed. You have to go to Northern Wake campus, RTP, Perry Health Sciences, one of those. If you are unable to make those, send me an email advance and we'll try to figure out an accommodation for you. But otherwise, you need to go schedule a time with the ELTC. I'll talk about that next week after you take the exam about how to do the scheduling with the ELTC. It's actually pretty straightforward, but again, just want to make sure you know how to do it. No one's watching today. Oh, actual question. Sorry. Quick question about sober rules. Is that something that we should know and have memorized? It's actually a Chem 1 concept. So yes, technically you should have already known this concept. That said, there are things in the notes to kind of help you. The big thing to memorize is the solubility rules. And particularly for this class, a good assumption to make is that if it doesn't have a solubility rule, it's insoluble. There are insolubility rules. The problem with insolubility rules is that there's so many exceptions to them. So the solubility rules, first one, anything that contains ammonium is soluble. Second, anything that contains a column 1 metal cation. And we have to specify the metal here. Hydrogen, something you have hydrogen in it, which is also column 1, is not automatically soluble in water, but lithium, sodium, potassium, rubidium, cesium, francium, every single one of those is soluble in water. Nitrate, acetate, and perchlorate. These are all soluble in water. Fourth rule, chloride, bromide, iodide, with 3 exceptions. Lead, silver, and mercury. So lead chloride, silver bromide, mercury iodide, mercury bromide, mercury chloride. These are all ones that are insoluble. Your last one, sulfate, accepts lead, silver, mercury, and calcium, barium, and strontium. So calcium sulfate, barium sulfate, and strontium sulfate are all insoluble in water. If it falls under any of these categories, it is soluble in water. If it doesn't have any of these, just treat it as insoluble. There are insolubility rules as well. I present them. They're not particularly useful because they do kind of say like, hey, if you have this and you don't have a solubility rule associated with it, then it's probably going to be highly insoluble water. So something like phosphates, carbonates, sulfides, things like that. My issue with the insolubility rules is that they're always trumped by the solubility rules. So if you have anything that meets one of those 5 requirements, it doesn't matter what the insolubility rule is, it's going to be there. The other thing is that these are kind of guidelines. So technically everything is soluble in water. So even calcium phosphate. This doesn't have a solubility rule. It's insoluble. It has an insolubility rule because of the phosphate, but we know it does this. And because we know it does this, it is technically soluble in water, it's just not very soluble in water. So really when we say something is insoluble in water, we just mean it's not very soluble in water. Like there is an upper threshold how much we can throw in there, but something like sodium chloride, you can throw sodium chloride in there until it's more sodium chloride than it is water. Yeah, just those 5 rules, and I tend to keep it pretty simple. Again, you should memorize them. I'm not a huge fan of making you memorize the insolubility rules because they're just not that helpful, but the solubility rules are kind of good to know. Actually, so another good reason to memorize the solubility rules, if you look at all the strong bases, they have a solubility rule associated with them. The exception being the hydroxides. So when we do test 4, you have to know the strong acids and the strong bases for that. They're super easy to memorize, especially if you know the solubility rules. Nitric acid, HNO3, nitrate soluble in water. Perchloric acid, HClO4. ClO4 has a solubility rule. Sulfuric acid, H2SO4, has a solubility rule. Hydrochloric acid, hydrobromic, hydroiodic, those are all strong acids, so they all have a solubility rule. There's actually only a handful of those solubility rules that don't come into play when it comes to the strong acids and strong bases. So yeah, good to know, but the insolubility. What are questions? Okay, so the shot radius principle, there's three forms of the shots. Um, and they can all be brought back to Q. But we have first one. So what Le Chat says is that if Q is greater than KEQ, where Q is less than KEQ, if Q is greater than KEQ, then we drive the reverse reaction. So basically, Le Chatelier says that if we have a reaction that is at equilibrium and we suddenly do something to make Q bigger, we're going to favor the reverse reaction, and for Q less than KEQ, we're going to drive the forward. So any reaction which is at an equilibrium and then is perturbed away from equilibrium will try to return to equilibrium. So there are three forms of this, and the easiest to see is concentration. So let's go back to the one from yesterday. Gas plus O2, gas, goes back and forth to 2, CO2, gas. Now we have an expression for Q here. That's the concentration of CO2 squared all over the concentration of CO squared concentration of O2. So at equilibrium, Q equals KQ. And if we make Q bigger than KQ, we're going to make the forward reaction more, we're going to make the reverse reaction more favorable. So there's two ways we can do this. To make Q bigger, we can make the concentration of the products bigger. So in this case, concentration of the products. But this is a ratio. So also, if we drop the concentration of the reactants, we can make this happen. So this is one of the first statements of Le Chatelier's. To drive the reverse reaction, we increase the concentration of the products or decrease the concentration of the reactants, because both will make Q bigger and bigger. Now, what's happening microscopically is that if we increase the concentration of the products, this is increasing the likelihood that these two CO2 molecules will react with each other and drive the reverse reaction. So this is just reaction kinetics. If we increase something, we increase concentrations, we increase the rate of reaction. Here we've got the rate of the forward reaction and the rate of the reverse. If this is elementary as written, the rate of the forward, which is concentration of CO squared, concentration of O2, minus the concentration of the reverse, concentration of CO2 squared. So if we increase the concentration of the products, we make this bigger, or if we decrease these concentrations, we make this smaller. In either case, we start favoring the reverse reaction because it becomes bigger relative to the forward reaction. The corollary here is that we can make Q smaller than KQ, and this will drive the forward reaction. And there's two ways to do this. We can decrease the concentration of the products, or we can increase the concentration of the reactants. And this is the same idea. If we increase the concentrations of these, we make the forward reaction more likely to happen. If we decrease the concentration of the reactants, we make this less likely to happen. But either way, the net effect is making the forward more favorable than the reverse. So this is the easiest forms of Le Chatelier's to see. The second is the pressure dependence. So if we look at the pressure dependence of this reaction, it's xCO2 squared, xCO squared, xO2, P naught over RT raised to, we've got 2 moles of products and 3 moles of reactants. So for this particular reaction, this ends up having a -1 pressure dependence. So Q is going to look like 1 over the pressure. So Le Chatelier says that if we increase the pressure of reaction, we're going to drive the direction that decreases the moles of gas phase. If we increase the pressure, if we decrease the pressure, we're going to favor the direction which drives the more moles of gas. The idea here is that at equilibrium, this is at an ideal pressure. So the problem with this corollary, which is a bit harder to see, is that it depends on the reaction. So in this case, we have a -1 pressure dependence. So as we increase pressure, Q goes down. And if Q becomes less than KQ, we favor the forward reaction. If we decrease pressure, we're going to increase Q. So as this gets smaller, this is going to get bigger, and so we favor the reverse reaction. Now conceptually what's happening is that there's only 2 moles of gas here and there's 3 moles of gas here. So if we increase the pressure, we can drop the pressure by creating more products because there's less moles of gas on this side. If we decrease the pressure, we would drive the reverse, and we would end up getting more moles of gas going this way. But let's say I had this reaction. Carbon solid goes to 2 CO gas. So now we have 1 here and 2 here. In this case, we'd have a +1 pressure dependence, and it would be the reverse. If we increase pressure, we increase Q, and so we drive the reverse reaction. So the thing about the pressure dependence is that you have to look at the reaction itself, and there's actually some reactions that have no pressure dependence whatsoever. So an easy example of this is the water-gas shift reaction. So H2O gas plus CO gas goes to CO2 gas and H2 gas. In this case, there's 2 moles of gas on both sides, so your pressure dependence here is 0, which means that if you change the pressure, it has 0 effect on the overall reaction. But that's the second form of Le Chatelier, which is the pressure dependence. The reaction, if pressure is increased, the reaction will shift to the side that has less moles of gas. If the pressure is decreased, it'll shift to the side that has more moles of gas. All this with the corollary that you assume that there's a pressure difference between left and right. If there's no gas phase species or there's the same moles of gas on both sides, there's no effect of pressure. Now the last one, which is a bit harder to see, is temperature dependence. So Le Chat says that as we increase temperature, we favor the endothermic direction. And if we decrease temperature, we favor the exothermic. So what this means is if you heat let's say you have a reaction. We'll bring this up again. This is very exothermic. Well, if it's exothermic in the forward direction, it's endothermic in the reverse. This is just the concept of microscopic reversibility. You can't have a perpetual motion machine. If it absorbs heat one way, it has to gain heat going if it releases heat one way, it has to absorb it the other and vice versa. So for this particular reaction, I know it's exothermic because it's combustion. So if I heat this reaction, it's actually going to go the reverse way. It's going to favor this side more. If I drop the temperature, I'm going to start favoring this side more. And the idea here being that it has an ideal temperature in that if you heat it, it's going to go in such a way to absorb the heat. If you cool it down, it's going to do something to replenish the heat. Now, there's actually a proof for this, and it's a bit harder to see. Because we have KQ equals E to the minus delta G over RT, and delta G here is delta H minus T delta S. So if we plug it all in, what we'll end up getting here is E to the minus delta H over RT times E to the delta S over R. So this delta S over R is just a constant. Let's call it phi. So we get E to the minus delta H over RT times our physical constant. The change in KQ with respect to temperature is just the first derivative of this. So we end up getting delta H over RT squared E to the minus delta H over RT. And this is going to be how Q changes with respect to temperature. So temperature is positive, delta R is positive, this whole term is positive. And this is the change. So all of this is just one big physical constant, delta H times some constant C. If delta H is negative, so this is an exothermic reaction, Q is going to get smaller as delta H increases. So at higher temperatures, Q is going to get smaller and smaller, which means that we're going to favor the reverse reaction. Something like that. But this is the proof for that relationship. But again, you're better to understand it. You can just go with the qualitative understanding. So all of that to talk about common ion effect. So with common ion effect, we write these idealized reactions. And a big example of this is acid-base chemistry. So let's say we have sulfurous acid. And this is a cute reaction to write. That should be 3. This is a cute reaction to write, but this really isn't what happens. What really happens is this HSO3 also dissociates into H plus and sulfide. So when we first start talking about equilibriums, we only keep it focused to one reversible reaction, but really there's usually multiple reversible reactions going on. But the thing is that these share a common ion, this bisulfite ion. So if I add sodium sulfite to the mixture, sodium sulfite just generates SO3 minus 2 plus sodium. It's an irreversible reaction. And what will happen is that the concentration, increasing the concentration here of sulfite by Le Chateliers will drive the increase of the bisulfate. But if we increase the bisulfate concentration, up here we start increasing the concentration of H2SO3. So even though we're not adding any, even though you don't see sulfite anywhere in this reaction, because it can be used to make or remove bisulfite, then adding the SO3 here does actually drive this reaction. So the common ion effect is basically a way of tethering a whole bunch of equilibrium reactions that are connected through what's called the common ion. And by affecting one reaction, because they share a common ion, we can affect one reaction and affect another. Another way you could do this is that magnesium sulfite is insoluble in water. So if we add magnesium chloride to sulfite, we would get MgSO3 plus 2Cl minus. But the thing is, if we add magnesium, it's going to start removing this sulfite. And so as you remove the sulfide, it drives the forward reaction. And the forward reaction will decrease the concentration of bisulfite. But since bisulfite's up here, since we're decreasing its concentration, we actually begin to drive the forward reaction up here. So this will begin to be removed as well. So by adding magnesium, we actually increase the acidity. We start increasing the H plus concentration because the magnesium is removing the sulfite, which consequently is removing the HSO3 minus because of this reaction. And you can definitely have super complicated equilibriums. You can have 5 or 6 systems that are all share a common ion and they all interplay on each other. We typically keep it just to 2. But that's how the common ion effect utilizes the Le Chatelier's principle. The Chatelier's principle tells you which way an equilibrium will go based on changes you make to that equilibrium with your abstract products, abstract reactants, change temperatures, change pressures. But because equilibriums can share reactants and products, shifting one equilibrium may inherently shift another equilibrium, and that's where the common ion effect goes in to say that, okay, well, if you mess with this one reaction that's equilibrium, because it shares an ion with another reaction, how does that affect the other reaction? Yeah, you're welcome. Oh, just me again. All right, doesn't seem like there's anybody else out there, so again, these are office hours. If you have questions, please feel free to email them in advance. Otherwise, these are here for you as a resource. Again, don't forget your exam is this week, and I will see y'all tomorrow.